Welcome to Introduction to IoT Design and Development Quadrant 3. Sorry, there is a spelling mistake. Today, first we are going to see IoT design methodology. And design methodology, the first step is purpose and requirements specification. Determining the system's goals and specifications comes first on the Internet of Things design process. Purpose, behavior, and requirements are documented at this stage. Step two, process specification. Defining the process specification is the second step in the IoT design process. Uh, in the IoT design, in the step three, IoT design process involves articulating the domain model. The domain model defines the key ideas, entities, and objects. The step three in the IoT design process involves articulating the domain model. The domain model defines the key ideas, entities, and objects that will be used in the development of the Internet of Things system. Object characteristics and inter-object connections are spelled out in a domain model. A domain model is a high-level platform agnostic representation of the IoT domains, concepts, objects, and entities. The designers of the IoT system can learn more about the IoT domain they will be working in with the help of the domain model. Phase involves a formal description of the IoT systems use cases that are derived from the purpose and requirement specifications. Step three in the IoT design process involves articulating the domain model. The domain model defines the key ideas, entities, and objects that will be used in the development of the Internet of Things system. Object characteristics and inter-object connections. Object connections are spelled out in a domain model. A domain model is a high level with the help of the domain model defining the information model is the fourth step in the IoT design methodology. The attributes of virtual entities, relations, etc. are all examples of information in the IoT system, and their structure is defined by the information model. Data representation and storage are not aspects of an information model. The information model is defined by first enumerating the virtual entities from the domain model. By specifying attributes and relationships, the information model enriches the definition of virtual entities. Defining the service specifications is the fifth step in the IoT design methodology. The services, service types, inputs, outputs, Endpoints, schedules, preconditions, and effects of an IoT system are all defined by its service specifications. The sixth step in the IoT design methodology is to specify the IoT level for the system. As the seventh stage of the IoT design process, defining the functional view is essential. The functional view categorizes IoT systems according to the tasks they perform. The concepts defined in the domain model are the focus of each functional group, which either provides the means for interacting with those instances or information about them. In the eighth stage of the IoT design process, we define the operational view specifications, options for the deployment and operation of the IoT system, such as service hosting, storage, device, application hosting, etc., are defined at this stage. Integration of devices and components is the ninth step. This is the step 9 of the Internet of Things design methodology. Step 10, application development. The final step in IoT design methodology is to develop the IoT application. Embedded system hardware is either a microcontroller or a microprocessor may serve as the brains of the embedded system. There is an IC in both of these varieties. A microcontroller from the RISC family, such as the Motorola 68 SC11, PAC 16 SC84, or Atmel 8051, is a crucial part of any embedded system. Internal read write memory is the primary feature that sets microcontrollers apart from microprocessors like the 8085. Below, we have outlined the core features and architecture of embedded devices. Embedded systems which rely on devices to run the OS typically perform real-time operations, and are founded on a language platform. Embedded software is developed by manufacturers for use in a wide variety of electronic products. An 8-bit microcontroller and basic lighting controls are two examples of simple embedded system software. Complicated software includes uh, includes things like that used to control missiles, factories, planes, and more. The goal of low-cost IoT devices necessitates careful consideration when selecting the microcontroller to ensure that its full set of features is put to good use. The characteristics of the microcontroller that are most relevant to your project are bit depth, how quickly and accurately microcontrollers perform non-trivial computations depends on the register and data path width. IoT is the emerging technology that will allow devices and people to exchange data and other information over the internet and IP enabled protocols. In contrast to the backend, which consists of processing and network connectivity interfaces, the front end consists of sensors that facilitate interaction with the physical world. Numerous racks are supported by the typical IoT system on chip. The following sections will be included: transmit and receive switch. RF part mainly consists of transmitter, receiver, oscillator, and amplifiers. Data and code can be stored in various memories, such as the programmed memory and the data memory. Depending on the system's complexity and latency needs, The physical layer can be handled by a field programmable gate array or MAC layer and upper protocol stacks, TCP, IP, etc. running on processor. Digital to analog converters and digital to digital converters serve as an interface between the digital baseband and the analog RF domains. Connectivity to the host can be achieved via a number of different interfaces, including SDIO, USB, SP, special peripheral interface, etc. The IoT system on chip can be used with a very wide variety of peripherals, including UART, I2C, GPIO, WDT, etc. When optimizing an IoT system on a chip that uses multiple wireless protocols and RF hardware to support multiple frequency bands, it is important to consider power consumption, data throughput, device size, the latency, and other aspects of performance. Redpoint Signals has recently designed and developed an IoT system on chip with model number RS9113. The same chip can function as a Wi-Fi access point, a Bluetooth 4.0 device, and a Zigbee device. Therefore, any of these wireless networks can be used to connect the IoT device. The IoT system on chip can be used for numerous applications: mobile M2M communication, real-time location finding tags, thermostats, smart meters, wireless sensor devices, serial to Wi-Fi converter, voice over Wi-Fi, compliant phones, home automation, healthcare devices, and equipments. Next, building blocks of IoT. Sensors, processors, gateways, and applications are the four main components of the Internet of Things. To function as a whole, the IoT relies on the unique qualities of each of these nodes. Sensors. This is the beginning of the Internet of Things. These entities are referred to as things in the system. Their primary function is either to receive information from its environment via sensors or to transmit information to its environment, actuators. These must be designed, these devices must be distinguished from others on a need to be dynamic in the wild so they can gather information in real time. Depending on the situation, these can function autonomously or be activated manually, network by having a special identifier such as an IP address. Next, processors. The IoT processor is the system's central processing unit. Their primary duty is to process the information gathered by the sensors so that usable information can be extracted from the mountain of raw data. One way to put it is that it grounds data with intelligence. Processors typically operate in a real-time fashion and are very amenable to being managed by software. These are also in charge of encrypting and decrypting information, ensuring its safety. The data is processed by embedded hardware devices like microcontrollers and other microelectronics. Gateways. The gateway's job is to take the processed data and deliver it to the right places so that it can be used effectively. Simply put, a gateway facilitates the sending and receiving of data. Connectivity to the data is provided via the network. For an Internet of Things system to function, network connectivity is mandatory. Access points in a network include the LAN, WAN, PAN, and anything else. Applications. The other component of an IoT system is applications. The data collected cannot be put to good use without the help of applications. The effective meaning of the collected data is rendered by these cloud-based applications. Users have full control over the applications that provide their desired services to their devices. Apps for automating the home, security systems, and industrial control lab, etc., are just a few examples of possible uses. In brief, we can detect that the data collected by the sending node and sending node undergoes initial processing before being transmitted via connectivity to the embedded processing nodes, which can be any embedded hardware device. Again, passing through the connectivity nodes, it is sent to the remote cloud-based processing, which can be any software, and then onto the application nodes where it will be used for its intended purpose and analyzed using big data. Yeah, then one main important question is how IoT works. How the IoT works is quite simple. To begin, it uses automatic identification and perception technologies like RFID, wireless sensors, and satellite positioning to gather data on objects, identifying characteristics and underlying infrastructure. Data is gathered in real time from sensors, RFID tags, and other things with the help of a centralized hub, such as a smartphone. Second, it integrates object related information into the information network and realizes the intelligent indexing and integration of the information related to the masses of objects by making use of fundamental research services by taking advantage of various forms of communication technologies. In the end, it analyzes and processes data related to large number of objects using technologies from the realm of intelligent computing such as cloud computing, fuzzy recognition, data mining, and semantic analysis in order to realize intelligent decision and control in the real world. All information gathered by the access system is sent to the internet devices via the physical layer. Once at the management layer, all the data is handled independently from the raw data via transmission lines. After all the data has been properly collected and managed, it is realized to the application layer. Arduino boards come in a wide variety, each tailored to a specific microcontroller. In any case, the Arduino IDE is used to write code for all Arduino boards. The inputs and outputs, processing speed, operating voltage, form factor, etc., differentiate one board from another. Some boards are made specifically for embedded systems and don't have a software interface. This requires additional investment in 3.7 volts batteries can power some devices while 5 volts is required for others. Various Arduino boards are detailed below. The Atmega 328 microcontroller used in Arduino boards. We'll get to know the Arduino board and all its parts inside and out. The Arduino Uno board will be the focus of this because it is the most widely used Arduino boards. It also the top board for novice programmers and electronics hobbyists. Even though some Arduino boards differ slightly in appearance from the Yeah, Arduino board can be powered by using the USB cable from your computer. All you need to do is connect the USB cable to the USB connection. Arduino boards can be powered directly from the AC mains power supply by connecting it to the board by connecting it to the barrel jack. The function of the voltage regulator is to control the voltage given to the Arduino board and stabilize the DC voltages used by the processor and other elements. The crystal oscillator helps Arduino in dealing with time issues. How does Arduino calculate time? The answer is by using crystal oscillator. The number printed on top of the Arduino crystal is 16,000 H 9H. It tells us that the frequency is 16 megahertz. You can reset your Arduino uh, board. You can reset the Uno board in two ways. First, by using the reset button 17 on the board. Second, you can connect an external reset button to the Arduino pin labeled reset. 3.3 volts, 6 pin supply 3.3 output volts, 5 volts, 7 pin supplies 5 output volt. Most of the components used with Arduino board works fine with 3.3 volt and 5 volt. GND ground 8 pin. These are several ground pins on the Arduino and any of which can be used to ground your circuit. Input voltage 9 pin. This pin also can be used to power the Arduino board from an external power source line AC mains power supply. Analog pins. The Arduino Uno board has 6 analog input pins A0 through A5. These pins can read the signal from an analog sensor like the humidity sensor or temperature sensor and convert it into a digital value that can be read by the microprocessor. Each Arduino board has its own microcontroller. You can assume it as the brain of your board. The main IC and the Arduino is slightly different from board to board. The microcontrollers are usually of the Atmel company. You must know what IC your board has before loading up a new program from the Arduino IDE. The information is available on the top of the IC for IC. For more details about the IC construction and functions, you can refer to the dataset. Mostly ICESP 12th pin is an AVR, a tiny programming header for the Arduino consisting of MDSI, MSO, SCK, reset, VCC, and ground. It is often referred to as an special peripheral interface, which could be considered as an expansion of the output. Actually, you are you are slaving the output device to the master of the SPI bus. Like that, we have all the power LED indicator, transmission and receiving LEDs, digital input output. AREF stands for analog reference. It is sometimes used to set an external reference voltage between 0 and 5 volts as the upper limit for the analog input pins. You will find detailed instructions on installing the Arduino IDE and preparing the board to receive the program over a USB cable. Step 1, the first things you will need USB cable, and an Arduino board. If you are using an Arduino product like the Evenvo, D Milano, Nano, or Mega. Mega 2560, also known as Dicimila, requires a regular USB cable, A plug to B plug, such as one would use to link a computer to a USB printer. The following the USB connection to the computer or an external power supply is automatically used to power the Arduino Uno. Mega, D Milano, and Nano. If you are using an Arduino Dicimila, the board must be set up so that it receives power from the USB cable. A jumper, a thin plastic piece that slides onto two of the three pins between the USB and power jacks, is used to switch between the two power sources. It should be on the two pins that are closest to the USB port, so check those. The Arduino board can communicate with the computer via a USB cable. The PWR indicator lighter, which is green, must be on. Unzipping the Arduino IDE folder is the first step after downloading the software. You will find the application icon inside the folder labeled Infinity application.exe. To launch the IDE, simply double-click its shortcut. Once the software starts, you have two options: create a new project, open an existing project example. To create a new project, select File New. To open an existing project example, select a file, example basics blink. Here we are going to take a look at one particular blink. It gradually activates and deactivates the LED. Choose one more one more case study from the available options. Select the correct Arduino board name which corresponds with the board connected to your computer. Is essential for a successful upload of your program to the board. Select your board by clicking Tools, then Board. Our tutorial assumes that you will be using an Arduino Uno, so we have gone ahead and given it that name. Determine which Arduino serial port to use. Use the menu items tool serial port. This is probably at least COM3 level. COM1 and COM2 are usually reserved for hardware serial ports. Disconnecting the Arduino board and then reopening the menu should reveal the answer. The entry for the Arduino board should be gone. To use that serial port again, reconnect the board. We need to show the purpose of each icon in the Arduino IDE toolbar before we can explain how to upload our program to the board. The value A is used to see if there was a problem during compilation. B employed in the process of loading software onto an Arduino board. C. New sketches can be made with the C shortcut. D. Used to jump to one of the illustrative sketches. E. To store your sketch. Press E. Serial monitor. F. Serial monitor that takes in data from the board and transmit it in the same format. Next, select upload from the context menu. If you give it a second, the board's RX and TX LEDs will begin flashing. Then uploading will be displayed in the status bar upon successful completion of the upload. Since its inception in 2005, the Arduino platform has been used to facilitate open source prototyping, flexible software development, and backend development, all while making it extremely simple to use for developers of all skill levels to create IoT solutions. Arduino is environment aware because it can take in input from a wide variety of sensors and communicate with other controllers to operate a wide range of machinery. The Arduino platform runs on a microcontroller that is integrated into the hardware. This platform allows for both independent and collaborative projects to be created through the use of additional resources such as tools and plugins. Open source software was used to create the IDE, which is compatible with Mac, Linux, and Windows systems. The Arduino platform, which is based on the processing programming language, appears to have been designed with novice users and experimentation in mind. Processing is an animation and Java virtual machine platform focused programming language used to create visual and interactive applications. Let us remember that this language was created with the intention of teaching students the fundamentals of computer programming in a visually visually accessible way. It's a free resource for anyone who wants to participate. All the apps are typically written in C, C++, and encapsulated in AVR GCC. The Arduino platform allows for analog to digital conversion and the attachment of sensor modules for measuring light, temperature, and sound. It is possible to use sensors like SPI or I2C to cover 99.99% of the market for these apps. Since Arduino is a microcontroller, typically the 8-bit Atmega microcontroller, and not a mini computer, it is not as feature-rich for experts. There is a large community of Arduino users to learn from and share knowledge with, as well as wide range of user manuals and project samples. Raspberry Pi designed in the United Kingdom by the Raspberry Pi Foundation and manufactured by Broadcom. The Raspberry Pi is a small single-board computer. Initially, the focus of the Raspberry Pi project was on spreading introductory computer science education in underprivileged communities. The first version ended up being more widely used than anyone had anticipated, especially in niches like robotics. Nikes like robotics. Its low price, modularity, and open design have led to its adoption in a variety of fields, including weather monitoring. After the launch of the second generation of boards, the Raspberry Pi Foundation established Raspberry Pi trading with Evan Upton at the helm to oversee product and technology development. The foundation's mission has been reviewed to focus on encouraging the dissemination of foundational computer science education in K-12 settings and underdeveloped regions. One of the most popular British computers is the Raspberry Pi. Several revisions of Raspberry Pi hardware have been released, each with its own unique combination of CPU type, RAM size, network connectivity options, and peripherals. Model A Plus, and the Pi Zero are all very similar to Model B and B Plus, but they lack the Internet and USB hub components. The Ethernet adapter plugs into a different USB port on the motherboard. The USB port in the Model A Plus, and Pi Zero is hardwired to the system on chip, while the Pi 1 Model B only has two USB ports. The USB Ethernet chip in the Pi 1 Model B Plus and later models include a 5-port USB hub, of which four are usable. A micro USB port serves as the Pi Zero's USB connection to the SoC. The Pi Zero lacks the 40-pin GPIO connector found on all other Pi boards, replaced it instead by solderable through holes. The Pi Zero WH fixes this shortcoming. The Pi 4 has a 1.5 GHz processor, while the Pi 3 model B Plus and 2 have 700 MHz and 1.4 GHz. The Pi 3 model B Plus and Two have 256 MB to 1 GB of RAM, while the Pi 4 has up to 8 GB memory, and the operating system are both stored on secure digital cards, especially micro SD HC cards. The bulletins carry between 1 and 5 USB ports. A standard 3.5 mm tip ring sleeve jack is provided for audio output, and both HDMI and composite video are supported for video output. Several general purpose input output pins provide low level output and are compatible with standard protocols like I2C, Wi-Fi 802.11n, and Bluetooth 4.4 are built into the Pi 3, Pi 4, and Pi 0W, while the beam models features an 8PAC Ethernet port. The Raspberry Pi is a tiny single board computer the size of a standard credit card. Its initial purpose was to aid in the teaching of computer science, but its use has since expanded. Raspberry has been a huge success for the company with over 8 million units sold since its inception. The Raspberry Pi 3 is the first single board computer to feature both Wi-Fi and Bluetooth connectivity and a 64-bit processor. It has been in the works for a year, says Eben Upton, CEO of the Raspberry Pi Foundation. A quad-core 64-bit 1.2 GHz ARM Cortex A53 chip, 1 gigabyte of RAM, video core 4 graphics, Bluetooth 4.1 and 8 2.11 in Wi-Fi replaced the Pi 3 in this variant. The developers assured that the new architecture improves performance by an average of 50% compared to the Pi 2. The Raspberry Pi GPIO ports are a low-level interface for autonomously controlling input and output, making it yet another unique feature. The connector on Raspberry Pi has 40 pins. The operating system of choice for Raspberry Pi is Linux. It also works perfectly with Android. Any virtualization system such as Gen Desktop enables the system to be used on Windows OS. It is possible to create software for the Raspberry Pi on a computer that requires installing a specialized tool chain, including an ARM compiler and libraries optimized for the ARM architecture, such as glib. Additional criteria that set apart various IoT platforms include scalability, customization, user friendliness, code control, integration with third party software deployment, alternatives, and data security. Modern Internet of Things platforms permit infinite scalability in terms of the number of connected devices. This ability is generally assumed for public uh, cloud deployments, but it should be rigorously tested for an on-premises deployment along with the platform's load balancing capabilities to ensure the server duster is operating at peak efficiency. Critical to the efficiency of the shipping process, it is related to openness of the platform source code, the availability of flexible integration APIs, and the loose coupling of the platform's components. Good application programming interfaces may be all that's needed for simple IoT solutions on a small scale. But in future-rich, rapidly evolving IoT ecosystems, developers typically need more regular access to the system's internals, including the code integration, interfaces, deployment options, data schemas, connectivity and security mechanisms, etc. Encryption, complete identity management, and adaptable deployment are all essential for data security. The fundamentals of preventing compromising breaches in your IoT solution include encrypting data at rest and in transit, authenticating devices, managing user access rights, and storing sensitive data in a private cloud. IoT platform provides offer two radically different models for deploying clusters of IoT solutions across these dimensions. The public cloud IoT PaaS and the self-hosted private IoT cloud. IoT cloud represents the culmination of the development of IoT platforms. These two terms are often used interchangeably, but when they are, it usually refers to an Internet of Things platform as a service. With this type of service, you can lease both cloud computing resources and an IoT platform from the same company. The provider may also provide pre-configured and pre-hosted Internet of Things solutions. However, the ability to create a private IoT cloud is a key feature of a contemporary IoT platform. Private IoT clouds, unlike public platform as a service solutions, can be deployed on any kind of cloud infrastructure, including on-premises data centers. Control over new feature development, personalization, and integration with third parties is greatly improved with this deployment method. Strict data security and performance standards are also in favor of this approach. Open source and built around user-friendly hardware and software. Arduino is a prototyping platform. The Arduino system consists of a programmable circuit board and the Arduino IDE software for writing and uploading computer code to the hardware. Arduino boards can take analog or digital input signals from a variety of sensors and use them to trigger a variety of actions from turning on off an LED to connecting to the cloud. Using the Arduino software, you can send a series of commands to the board's microcontroller, allowing you to manage the board's functions. To upload new code onto an Arduino board, you don't need a separate piece of hardware, unlike with older programmable circuit boards. A USB cable can be used instead. In addition, the Arduino IDE employs a tamed version of C++ that facilitates learning. Arduino, with its standardized form factor, simplifies access to the microfutures controllers. If you are building connected devices and smart things, a premium IoT platform should give you access to most of the IoT functionality you need across the four typical layers of the IoT stack: things, connectivity, core IoT features, and applications and analytics. Either directly or via an Internet of Things gateway, your devices will communicate with the platform, which will be located in the cloud or in your on-premises data center. If your endpoints if your endpoints contact to the cloud directly, or if you need local processing power, for instance, a gateway would be useful. An IoT gateway can also be used to translate protocols such as when your devices are connected to a LoRaWAN network but must use MQTT to talk to the cloud. The components of an Internet of Things platform can be separated out individually. The foundation is the platform's underlying infrastructure, which allows it to function components for managing containers, messaging within the platform, orchestrating clusters of IoT solutions, and more are all available here. To put it in another way, devices connect to the cloud to carry out various tasks via the communication layer, which enables messaging for the device. The next layer describes the foundational Internet of Things capabilities offered by the platform: data collection, device management, configuration management, messaging, and over-the-air software updates are just a few examples of these crucial functions. There is an additional layer on top of the fundamental capabilities of the Internet of Things that has less to do with communication between devices and more to do with platform processing of this data. There is a reporting feature that lets you make your own reports. Data in user applications can be represented visually. Then your IoT solution has a rule engine, analytics, and alerting to let you know about any unexpected behavior. The most effective Internet of Things platforms also provide integration with other systems and the ability to install custom software. Without this adaptability, it could be prohibitively expensive and time consuming to tailor an IoT platform to a specific business scenario. IoT platforms are multi-layer technologies that make the Internet of Things simpler by facilitating the provisioning, management, and automation of interconnected devices. In essence, it utilizes a wide range of data processing capabilities, enterprise-grade security measures, and a variety of connectivity options to link your hardware of varying types to the cloud. IoT platforms offer developers a suite of pre-built tools that simplify and expedite the creation of scalable cross-device applications for the Internet of Things. Therefore, an Internet of Things platform can serve multiple purposes. When discussing its role in establishing connections between distributed devices, the term middleware is often employed as well as all the interactions between the hardware and the application layers to user applications. Its primary value to businesses lies in its ability to provide common devices with access to cloud-based applications and services. Hence, its other names Cloud Enablement Platform and Internet of Things Enablement Platform. Finally, it rebrands itself as an essential resource for Internet of Things developers under the moniker IoT Application Enablement Platforms. The original form of IoT platforms was IoT middleware, whose job it was to act as a go-between for the hardware and application layers. Its primary functions included gathering information from devices using a variety of protocols and network architectures, controlling and managing devices remotely and updating their firmware wirelessly. IoT middleware in real-world heterogeneous IoT ecosystems is expected to support integration with virtually any connected device and to blend in with the device's existing set of third-party applications. Because of this ability to abstract away from specific hardware and software, a single IoT platform can be used to manage any type of connected device. The hardware and application layers also benefit from the many new projects introduced by modern IoT platforms. They supply parts for the user interface analytics, data processing on the device, and deployment in the cloud. Some of them are capable of implementing complete Internet of Things services from the ground up. RFID tags, sensors, and other electronics make up this IoT relies on to function. Wireless sensor networks consist of non-wired devices like RFID tags and sensors. Since sensors are dynamic, data collection and processing must occur in real time. The raw data is transmitted from this layer via its network connectivity to the gateway and network layer. The requirements of what is commonly referred to as big data are simply beyond the capabilities of conventional data management systems. As we have seen throughout IoT's true worth lies not in the connections themselves, but in the data generated, the new services they make possible, and the insights they provide into how to run a business. However, the information can only be of use if it is handled in a structured and managed fashion. Therefore, the states a different strategy for data analytics. Massive amounts of data creation from sensors is a common problem in the Internet of Things, both in terms of transportation and data. The commercial aviation industry and the sensors installed throughout an aircraft provide a great example of the avalanche of data that can be generated by IoT. There are thousands of sensors in today's jet engines and they produce 10 GB of data every second. It is plausible that a commercial aeroplane could generate a petabyte of data in a single day. About 100,000 commercial flights take off every day around the world. Even just the commercial airline industry generates a massive amount of Internet of Things data. This is one case that demonstrates how the Internet of Things is exacerbating the already serious issue of big data. The data analytics are the field that find the most effective means of analyzing this mountain of information. For the Internet of Things to deliver on its promise, data analytics must quickly provide useful insights and knowledge from any type of volume of data. It's important to define a few key concepts related to data before delving deeper into data analytics. One reason is that data can be organized into different types and hence subject to various interpretations. With this, I'm going to end this third quadrant session. We will continue in quadrant four. Thank you.